So this is my solution now, that at this point, because this is already austenite, solid, so solid will be in grains. So you just show some grains, but each grain is only gamma austenite. Once it reaches here, then on the grain boundaries, we have told you that the new material will always form on the grain boundaries. So on the grain boundary, some alpha has started to form. When it goes here, then all these grain boundaries become very thick with alpha, right? Some gamma is still there, but this dot dot of alpha have become very thick lines of alpha. Now, as soon as it touches this temperature, 723, then whatever gamma was there has changed into perlite. Perlite was alpha and cementite, right? So this is what you draw. But there is one very critical thing. You see, there is alpha which is forming here and which is forming here. So all this alpha is above this temperature. This temperature is eutectoid temperature. So all this alpha is pro-eutectoid alpha. Pro-eutectoid, formed at above eutectoid temperature. And in the perlite, there is again alpha and cementite. So in the perlite, you write eutectoid ferrite and eutectoid cementite, right? So this I am mentioning separately, that you see this is the temperature. So you should write pro-eutectoid, not eutectic, pro-eutectoid alpha, eutectoid cementite, and so on. So again, right, this is not that this is something which you should do only in one course. I keep on reminding you that this habit that we do a course very well, some of you get B, some B plus, some A minus, some A, and the next time you say we don't remember anything. You see, the basics must be there, because that is why we do manufacturing after we make you do materials. That is why we do final year project after you have done materials and manufacturing and design, right? So that knowledge can be used later on. So your manufacturing will always be weak if your materials was weak. So this was a repeat, but it was not unexpected. We had kept on telling you that this is a portion which you revise, please, and we will ask you about it. Okay, let's move further. Now this is a numerical portion of the same. For A you just had to draw, but for B is saying the amount of tin in a lead tin alloy, phase diagram shown below, is 40 weight %. Amount of tin. What is the amount of eutectic alpha in this alloy at room temperature? At room temperature. So now this phase diagram is given lead, tin, and weight % tin is moving here, weight % tin. Of course, I keep on reminding you that it is mass %, but I mean technically whatever we say. And here it is all liquid, alpha on this side, beta phase on this side. So alpha plus liquid here, beta plus liquid here, eutectic point, and here below at any temperature here it is alpha plus beta. So 40 weight % tin, this is your starting. So at 40 make a straight line, at 40 make a straight line. This is it, at 40 make a straight line. Now we tell you that if you want to solve any problem, then make a vertical line here and draw a horizontal line at whatever temperature we are asking the question. Draw a horizontal line at whatever temperature we are asking the question. When we say room temperature will be say something here. If you draw a horizontal line here, it does not cut anything anywhere. So you are in a big fix. So here was the only small trick part. And we had explained it to you many times in lead tin alloy, in copper nickel alloy, in iron carbide steel diagram. You see, when, for example, if it is 40 weight %, you are coming from here, it is all liquid. When you touch here, it starts to become some alpha, more alpha, more alpha, more alpha. When you touch this line, whatever liquid is remaining changes into alpha plus beta. So just below this temperature, this is 183 Celsius, just below this temperature, all the changes have been completed. You see, you are coming from here, liquid, some alpha, more alpha, more alpha, more alpha, more alpha, If you have any temperature here, you draw a horizontal line to find out how much alpha, how much this. Once you touch this line, the left point is this one, the right point is this one. So, right, and if you are just below this, so now the left point is here, the right point is here. So just below 183 Celsius, whatever change in the structure is happening has happened, already happened. So now whatever percentage, everything remains the same. If you just cool down, then you just change the temperature. So your calculation should be just below 183 Celsius. Just below 183 Celsius. And whatever you get there, after cooling to room temperature, it will remain the same. Right? So this was the only understanding part. And we had explained this point many times during the lectures. That on any phase diagram, the lowest point is that solidus line, horizontal solidus line. Once you are just below that line, do all the calculations. After that, you just change the temperature. There is no change in composition and structure below that line, right? So I am explaining this to you in a lot of detail. Again, because this is phase diagram and every casting is some phase diagram of some alloy. So after you explain this, then just have a look that you see to find out. Remember this small something, that if you want to find, you see whatever you find at this time is the total alpha. Remember there is pro-eutectic alpha, and there is eutectic alpha. So eutectic alpha is total minus pro-eutectic. This is the key. Any alpha formed here is total alpha. So if you want to find the eutectic alpha, then this total alpha minus the alpha formed above. So you have to do a calculation just above 183 and a calculation just below 183. And when you do both of them, which is now very simple, then your answer will be there. So you see, had you revised a few of these things, then this would be very simple. But those of you who did not, right, then they had some problem, but a lot of you got it completely right also, mashallah. So we have already showed you all these steps, that this is your alloy. At 40% we have drawn a line. Just make a tie line at 183 plus something, right? So here, if you want to find pro-eutectic alpha, it will be 61.9 minus 40, right, upon 61.9 minus 18.3. So this is at 183 plus delta T. Then just below 183 minus delta T, left point is here, right point is there. So now the total alpha is opposite side, 97.8 minus 18.3 upon, 97.8 minus 40 upon total, right? So this is there. So this is pro-eutectic alpha, this is total alpha, right? So eutectic alpha is total minus pro-eutectic, and this is your percentage. So once again, right, that this is calculation wise not a big question, just 5 minute, 10 minute maximum, but understanding wise, two main things, that which we explained in the part A also, right? Part A was iron carbide, but above a certain temperature, whatever phase you form is pro-eutectoid or pro-eutectic. Below it is, so total is a sum of these two. There are two types of alpha, right? There is liquid here, there is alpha here. So this alpha is pro-eutectic alpha, and there is alpha here, which is eutectic alpha. So this was the solution.